July 2, 1941, Kummersdorf Proving Grounds, 25 kilometers south of Berlin. The pencil in Oberingenieur Wolfgang Fischer's hand stopped moving mid-calculation. For the third time that morning, he rechecked his measurements of the armor plate thickness. The numbers defied German engineering doctrine. The Soviet T-34's frontal armor, sloped at 60 degrees from vertical, provided an effective thickness of 90 millimeters, while using only 45 millimeters of actual steel. German tanks achieved similar protection only with 80 millimeters of vertical armor, nearly twice the weight. Fischer set down his calipers and stared at the captured Soviet tank, its green camouflage still bearing the scars of battle from the fighting near Grodno 8 days earlier. In his 20 years designing military vehicles for Henschel and Son, he had never encountered such elegant simplicity achieving such devastating effectiveness. The T-34 had arrived at Kummersdorf after being captured intact on June 24th, one of the first specimens taken during Operation Barbarossa's opening days. Now Germany's finest engineers swarmed over it like archaeologists discovering an impossible artifact. What they found would shatter their assumptions about German technical superiority and trigger a crisis of confidence that would reshape the entire German tank program. The mathematics of armored warfare were being rewritten by a nation the Wehrmacht had dismissed as technologically primitive. Each measurement, each test, each discovery pushed German engineers further from their comfortable certainty and closer to an admission they never thought they would make. The first encounter had occurred on June 23, 1941, near Grodno, when Unteroffizier Klaus Weber of the 7th Panzer Division met the future of armored warfare. His Panzer III platoon spotted a lone Soviet tank approaching across an open field. Weber ordered his gunner to engage at 500 meters, a range where German marksmanship typically guaranteed a kill. The 37mm armor-piercing round struck the Soviet tank's turret and bounced off harmlessly. Weber ordered rapid fire. 7 more rounds struck the approaching tank, each one ricocheting into the sky. The Soviet tank continued advancing, apparently unaware it was under fire. At 200 meters, the Soviet tank's gun fired once. The Panzer III to Weber's left exploded. Its 30mm armor penetrated completely. The Soviet tank fired again, destroying another Panzer III. Weber's driver threw the tank into reverse, retreating at maximum speed while the gunner continued firing futilely at the impervious enemy machine. Only a lucky hit on the Soviet tank's track finally immobilized it, allowing German infantry to approach and destroy it with bundled grenades. When Weber examined the knocked-out vehicle, he found 29 impact marks from German shells. Not one had penetrated. This was the Wehrmacht's introduction to the T-34. Within days, similar reports flooded in from across the entire Eastern Front. Panzer crews described Soviet tanks that seemed immune to German weapons, that could traverse swamps where German tanks bogged down, that appeared suddenly from forests German commanders had deemed impassable for armor. The scale of the crisis became apparent through ammunition expenditure. In the first 3 months of Barbarossa, German forces fired more anti-tank rounds than in all previous campaigns combined, yet tank kill ratios remained dismally low. A study by the Wehrmacht's Statistical Office in September 1941 revealed that German tanks required an average of 13 hits to destroy a T-34, while T-34s typically destroyed German tanks with 1 to 2 hits. This 13-to-1 disadvantage in ammunition efficiency had catastrophic implications for German logistics, already strained by the vast distances of the Russian front. The Wehrmacht's Quartermaster General, Eduard Wagner, noted in his diary that anti-tank ammunition consumption was 450% above planned rates, primarily due to rounds failing to penetrate T-34 armor. German industry, already operating at capacity, couldn't increase ammunition production sufficiently. By August 1941, frontline units were rationing anti-tank rounds, forcing crews to engage T-34s only at point-blank range where penetration was marginally possible. General Heinz Guderian, architect of German blitzkrieg doctrine, personally investigated these reports near Mutsensk on October 6, 1941. What he witnessed challenged everything he believed about armored warfare. A handful of T-34s from Colonel Mikhail Katukov's 4th Tank Brigade, attacked the 4th Panzer Division, destroying dozens of German tanks while suffering minimal losses. Guderian watched through binoculars as German 37mm and 50mm shells bounced off T-34s at point-blank range, while return fire from the Soviet 76.2mm guns destroyed Panzer IIIs and I-4s with single shots at distances exceeding 1,000 meters. In his memoir, Guderian wrote with unusual candor about this engagement. The rapid advance on Tula which we had planned had to be abandoned. Our casualties were severe. What made things worse was that the enemy's new tanks were superior to ours in armor and armament. The short-barreled 75mm gun of our Panzer IV was effective only if the T-34 was hit from behind on the gearbox. Neither the 37mm nor the 50mm gun could penetrate the T-34's armor at normal combat ranges. The Russian 76.2mm gun, on the other hand, could penetrate our tanks at distances up to 2,000 meters. The psychological impact on German tank crews was immediate and devastating. Feldwebel Hans Becker of the 11th Panzer Division recorded in his diary on July 3, 1941, "We have been deceived. Our leaders told us the Russians had only obsolete equipment. Today I watched 5 of our tanks destroyed by a single Russian tank we couldn't even damage. My gunner, Wilhelm, fired 23 rounds. Each one bounced off. Wilhelm wept. A hardened soldier who survived France and Greece, reduced to tears by his helplessness." By late June 1941, the German High Command could no longer ignore the crisis. Hitler himself demanded answers, refusing to believe that Soviet engineering could surpass German technology. A special commission was formed, led by Ferdinand Porsche, designer of the VK 45.01P that would become the Tiger tank prototype, and including engineers from Henschel, MAN, Daimler-Benz and Krupp. Their mission was to examine captured T-34s and determine how an allegedly backward nation had produced such a superior fighting machine. The examination team at Kummersdorf included some of Germany's most brilliant engineering minds. Besides Wolfgang Fischer from Henschel, there was Dr. Erwin Arders from Daimler-Benz, Heinrich Ernst Kniepkamp from the Army Weapons Department, and Professor Ferdinand Porsche himself. Each man arrived confident that detailed analysis would reveal critical weaknesses that German crews could exploit. Instead, they discovered a masterpiece of practical engineering that challenged their fundamental assumptions about tank design. The impact on German manufacturers was immediate and profound. At Henschel and Son, the entire VK 36.01 heavy tank project was scrapped after engineers realized its vertical armor was obsolete. The company lost 6 months of development work and 12 million Reichsmarks in investment. Porsche's competing design faced similar cancellation, with Ferdinand Porsche himself admitting in a private letter that the Russian tank has made 2 years of our work worthless overnight. At Daimler-Benz, the shock was particularly acute. The company had just received contracts for expanded Panzer III production when the T-34 rendered their entire product line obsolete. Chief Engineer Fritz Nallinger convened emergency meetings where engineers openly discussed copying Soviet design features, something unthinkable weeks earlier. The company's internal correspondence reveals near panic, with one memo stating, "We are at least 2 years behind Soviet tank development, possibly more." Mann's response was more measured but equally dramatic. The company immediately began recruiting engineers from civilian automotive projects, recognizing that incremental improvements to existing designs were insufficient. They established a special T-team, dedicated solely to analyzing captured T-34s and developing countermeasures. This team would eventually design the Panther, but not before experiencing what they called the humiliation of studying superior enemy equipment. The armor analysis revealed revolutionary thinking that German engineers had dismissed as theoretically inferior. By sloping armor at 60 degrees, Soviet designers achieved equivalent protection with half the weight of steel. Dr. Aders calculated that a shell striking the sloped armor had to penetrate the equivalent of 90 millimeters, while the actual plate was only 45 millimeters thick. Furthermore, the extreme angle increased the likelihood of ricochets, with many rounds simply skipping off the surface without transferring energy to the armor. Wolfgang Fischer spent 3 days measuring and analyzing the T-34's armor configuration. His report to the Commission stated, "The entire design philosophy contradicts our approach. We add armor thickness for protection, adding weight that requires larger engines and stronger transmissions. The Soviets achieve superior protection through geometry, not mass. A Panzer IV requires 3,200 kilograms of armor to achieve the protection this T-34 obtains with 1,900 kilograms. We have been thinking in 2 dimensions while they designed in 3. The hull design revealed brilliant simplicity that shocked engineers accustomed to complex German construction. The T-34's hull consisted of just 4 main plates, all sloped optimally, eliminating the shot traps that plagued German designs where incoming rounds could be deflected into vulnerable areas. Heinrich Kniepkamp noted, "This hull could be produced by moderately skilled workers with basic equipment. Our Panzer III hull requires master welders and precise jigs. The Russian design achieves superior performance with inferior manufacturing resources." The suspension system provided another revelation. German tanks used leaf spring suspensions inherited from automotive design, limiting wheel travel to 150 mm and causing a harsh ride that fatigued crews and restricted cross-country speed. The T-34 employed a Christie suspension with large road wheels and long-travel coil springs. Each wheel could move independently over a vertical distance of 500 mm. This allowed the T-34 to maintain 35 km per hour over terrain that forced German tanks to slow to 10 km per hour. Professor Porsche personally tested the suspension by driving the captured T-34 across Kummersdorf's obstacle course. His test report read, "The vehicle crossed trenches that would trap our Panzer IV. It climbed slopes that our tanks cannot attempt." The ride quality surpasses anything in our inventory. The gunner can actually aim while moving, something impossible in German tanks except on roads. We have fundamentally misunderstood the requirements of mobile warfare. The track system presented innovations that solved problems German engineers hadn't even recognized. German Panzer III tracks were 360 mm wide, resulting in ground pressure of 0.92 kg per square centimeter. The T-34's 550 mm tracks reduced ground pressure to 0.64 kg per square centimeter. This seemingly small difference had enormous tactical implications. During the autumn rains of 1941, entire German panzer divisions became immobilized in mud while T-34s continued operating. Dr. Ernst Hoffmann from Maybach analyzed the track system extensively. The Soviet designers had used manganese steel tracks that maintained their properties at -40 degrees Celsius, while German tracks became brittle at temperatures below -20 degrees Celsius. The track pins featured a simple but ingenious design, allowing field replacement in minutes using only a hammer. German tracks required depot-level maintenance for similar repairs. Hoffmann wrote, "Every aspect reflects experience with the Russian environment. They designed for their reality while we designed for our theories." The engine compartment yielded perhaps the most surprising discoveries. The T-34 used a V2 diesel engine producing 500 horsepower from a compact, robust design weighing 750 kilograms. The engine was made of cast iron and steel using manufacturing techniques German engineers considered crude. Yet this crude engine proved more reliable than sophisticated German power plants. The diesel fuel provided multiple advantages: 50% lower fire risk compared to gasoline, 30% better fuel efficiency providing greater operational range, and the ability to run on various fuel grades including kerosene, crude oil, and even alcohol in emergencies. Wolfgang Fischer studied the engine design for a week, documenting every detail. The V2's design philosophy contradicted everything taught in German engineering schools. Large tolerances between moving parts allowed for thermal expansion and contamination. Rough casting surfaces that would fail German quality control worked perfectly adequately. Simple splash lubrication replaced complex pressure systems. Fischer later wrote, "We Germans prided ourselves on precision engineering, components machined to tolerances of hundredths of millimeters." The V2 engine has tolerances 10 times larger, yet it works reliably in conditions that destroy our engines. They designed for mass production and field maintenance. We designed for perfection in a laboratory. Their approach works in war. The transmission system shocked German engineers with its robust simplicity. The T-34 used a simple 4-speed gearbox that could be operated by minimally trained drivers. It lacked the synchronized gears and precise machining of German transmissions, but proved far more reliable under combat conditions. The clutch was deliberately designed to slip under extreme loads, protecting the transmission from driver error. German systems, engineered for maximum efficiency, would destroy themselves if abused. A Soviet driver could shift gears wrongly, ride the clutch, or stall the engine repeatedly without damaging the transmission. German tanks required skilled drivers to avoid catastrophic mechanical failure. The gun system provided crucial insights into Soviet design philosophy. The 76.2mm F-34 gun was a masterpiece of practical engineering. While less precisely manufactured than German weapons, it exceeded German tank guns in the metrics that mattered. The bore was chrome-plated, extending barrel life to 5,000 rounds compared to 2,000 for German guns. The recoil system used a simple hydraulic buffer that could be repaired in the field. The gun's dual-purpose capability, firing both armor-piercing and high-explosive rounds with equal effectiveness, surpassed the specialized German approach, requiring different guns for different roles. Dr. Friedrich Krüger from Krupp studied the ammunition extensively. His findings challenged fundamental German assumptions. The Soviet armor-piercing rounds are simple, solid shot, relying purely on kinetic energy. Our complex, armor-piercing ballistic capped rounds are theoretically superior, with better aerodynamics and penetration angles. But they require precise manufacturing that limits production. The Soviet rounds achieve 90% of our performance at 30% of the cost and complexity. In a war requiring millions of rounds, their approach is superior. The turret design exemplified Soviet manufacturing efficiency. Cast as a single piece, it eliminated the numerous welds required in German turrets, each weld being a potential weak point. The casting process allowed for variable thickness, with 75 mm of armor facing forward, 52 mm on the sides, and 30 mm on top, optimizing protection versus weight. German engineers had rejected casting, believing the process created brittleness. Soviet metallurgists had solved this problem through heat treatment techniques German industry hadn't developed. The crew ergonomics initially seemed inferior to German standards. The T-34 was cramped, with the driver and hull gunner/radio operator squeezed into the hull, while the commander/gunner and loader worked in the tight turret. Vision devices were minimal, communication systems basic, yet extended testing revealed deliberate choices behind apparent deficiencies. The cramped interior minimized the tank's silhouette, presenting a target 30% smaller than comparable German tanks. Limited vision devices were adequate for Soviet tactical doctrine emphasizing mass attacks rather than individual tank duels. Simple controls could be operated while wearing heavy winter mittens, impossible in German tanks with their precise but delicate switchgear. Lieutenant Colonel Hans Schäfer, assigned to evaluate crew efficiency, reached a startling conclusion after extensive testing. The T-34 is not designed for comfort or individual excellence. It is designed for mass production and operation by conscript crews with minimal training. A peasant who has driven a tractor can operate a T-34 after 2 weeks of training. Our tanks require 3 months minimum to achieve basic proficiency. In total war mobilizing millions, their approach is mathematically superior. The manufacturing analysis proved most psychologically devastating to German assumptions of technical superiority. The T-34 incorporated numerous innovations enabling mass production. Parts were designed with huge tolerances, allowing components from different factories to be intermixed. Critical dimensions were standardized across multiple components, reducing the variety of tooling required. Subassemblies were designed for testing before installation, catching defects early in production. Dr. Wilhelm Bauer from MAN conducted detailed production analysis. A Panzer III required approximately 6,000 man-hours to build in 1941. The T-34 initially required about 8,000 man-hours, but Soviet production improvements rapidly reduced this. By 1943, Chelyabinsk tractor factory was producing T-34s in 3,700 man-hours, while German tank production times increased due to growing complexity. The Panther required over 150,000 man-hours, the Tiger 250,000. Bauer's report stated, "Soviet factories can produce 2 T-34s for every Panzer we build." Given the Soviet Union's larger industrial workforce and multiple production facilities, the actual ratio could reach 4-1. Mathematics, not tactics, will determine this war's outcome. The T-34's design team, led by Mikhail Koshkin at factory number 183 in Kharkov, had approached tank design from first principles rather than evolutionary development. Unlike German designers who refined existing concepts, Koshkin's team questioned every assumption. Why must tanks have vertical armor? Why use gasoline engines? Why prioritize crew comfort over production simplicity? Why build tanks only specialized factories could produce? Their answers revolutionized not just tank design, but military manufacturing. Philosophy. Koshkin himself was dying of pneumonia contracted during winter testing when the T-34 entered production. He insisted on continuing work from his sickbed, reviewing production reports and design modifications until his death in September 1940. His deputy, Alexander Morozov, seamlessly continued development, demonstrating another Soviet advantage: design continuity through systematic documentation rather than individual genius. German design teams, centered on prominent personalities like Porsche and centered on cult of personality, struggled when key individuals were unavailable. The Commission discovered that T-34 development began in 1937, with prototypes tested extensively in combat conditions during the Winter War against Finland. While Germany celebrated bloodless victories using tanks designed in the early 1930s, the Soviet Union was already mass-producing a revolutionary design incorporating combat lessons. By July 1941, Soviet factories had produced over 1,200 T-34s, with improved models already in development. German intelligence had dismissed reports of new Soviet tanks as propaganda. This intelligence failure cost thousands of German tank crew lives. Testing revealed seemingly minor details with major implications. The T-34's air intake system used a cyclone filter that removed dust particles through centrifugal force. German tanks used felt filters requiring frequent cleaning and replacement. In the dusty conditions of summer 1941, German tanks required filter changes every 100 kilometers. T-34s operated for 1,000 kilometers without maintenance. This tenfold difference in maintenance intervals had strategic implications during rapid advances. The driver's hatch design demonstrated Soviet attention to combat reality. It could be locked partially open, providing ventilation and visibility while maintaining protection against shell fragments. German hatches were either fully open, exposing the crew, or fully closed, limiting visibility. Soviet designers understood that combat involved long periods of movement where partial protection was optimal. German designers had optimized for the brief moments of tank versus tank engagement. Winter testing in January 1942 demonstrated crushing Soviet advantages in cold weather operations. The T-34 started reliably at -40 degrees Celsius using a compressed air system that didn't depend on battery power. German tanks required external heating or hand cranking in extreme cold. The T-34's wide tracks distributed weight, allowing movement over snow that trapped German tanks. Track grousers could be installed in minutes to improve ice traction. German tanks required hours to install similar devices. The diesel engine's cold weather advantages exceeded mere starting reliability. Diesel fuel didn't evaporate like gasoline, reducing fire risk when tanks were hit. Diesel exhaust was less visible than gasoline exhaust in cold air, reducing detection risk. The engine warmed up faster due to higher compression, allowing quicker combat readiness. German crews spent hours warming engines while T-34s were already maneuvering. Ammunition storage revealed another Soviet innovation. Rounds were stored low in the hull beneath the turret floor, reducing the likelihood of catastrophic explosion if penetrated. German tanks stored ammunition along hull sides where any penetration could trigger explosion. The T-34's ammunition was also protected by rubber mats that prevented sparks from igniting propellant. German tanks used metal racks that could create sparks when struck. The Commission's examination extended to captured Soviet technical manuals and production documents. These revealed a sophisticated understanding of statistical quality control that German industry hadn't implemented. Soviet factories used sampling inspection and statistical process control, concepts developed in America but not yet adopted in Germany. This allowed quality maintenance despite using less skilled workers. German quality depended on individual craftsmanship, impossible to maintain with conscript labor. By November 1941, the Commission faced a terrible reality. The T-34 wasn't just superior to current German tanks, it represented a design philosophy German industry couldn't readily adopt. Copying the T-34 directly, as Porsche proposed, was impossible. German factories were tooled differently, German workers trained differently, German military doctrine evolved differently. Germany needed its own answer to the T-34, but that answer would take years to develop and deploy. The Commission's interim report to Hitler in December 1941 walked a careful line between honesty and survival. They couldn't directly state Soviet superiority without risking accusations of defeatism. Instead, they recommended immediate development of new tanks incorporating lessons learned from combat experience. This bureaucratic euphemism masked fundamental admission of German inferiority. The report triggered the development programs that would produce the Panther and Tiger, but these wouldn't reach the battlefield in significant numbers until 1943. Two competing designs emerged for Germany's T-34 response. Daimler-Benz proposed essentially copying the T-34, including rear transmission, diesel engine, and sloped armor. MAN proposed a more conventional German layout, but incorporating sloped armor and enhanced firepower. The MAN design was selected, becoming the Panther. However, the Panther reflected persistent German inability to embrace Soviet design philosophy. Where the T-34 weighed 26 tons, the Panther weighed 45 tons. This weight increase cascaded through every system: heavier transmission, wider tracks, larger engine, more fuel consumption, reduced strategic mobility. Intelligence reports in early 1942 revealed the scale of Soviet T-34 production. Factories evacuated from western regions were reaching full production in the Urals. Chelyabinsk tractor factory, nicknamed Tankergrad, was producing 500 T-34s monthly by March 1942. The Stalingrad tractor factory, despite being under aerial bombardment, continued producing tanks that drove directly from the assembly line to the battlefield. German bombing couldn't stop production dispersed across multiple facilities. The T-34's influence on German tank crews was documented in censored letters home. Gefreiter Friedrich Müller wrote to his wife, "We no longer feel like warriors but like targets. Every time we see that distinctive sloped silhouette, fear grips our hearts. Our shells bounce off while theirs punch through our armor like paper." Lieutenant Hans Bergmann recorded in his diary, "The psychological burden of fighting in inferior equipment is breaking my men. They know that engaging a T-34 is likely suicide unless we achieve complete surprise. Training materials were hastily revised to address T-34 vulnerabilities. Crews were instructed to target tracks, vision devices, and the turret ring. These tactics acknowledged German inability to penetrate T-34 armor at normal combat ranges. The proud Panzer force was reduced to mobility kills and mission kills rather than outright destruction. Even these modest goals required numerical superiority and tactical advantage. By spring 1942, German engineers were studying T-34 manufacturing techniques more intensively than combat capabilities. How did Soviets achieve consistent quality with unskilled labor? How did they maintain production while relocating entire factories? How did they incorporate improvements without disrupting production? The answers challenged German industrial culture at its core. Soviet designers had optimized for the constraints of total war: limited skilled labor, disrupted supply chains, massive scale requirements. The T-34-85, introduced in 1944, demonstrated Soviet ability to evolve the design without fundamental changes. The larger turret accommodated 3 crew members, addressing the commander-gunner dual-role weakness. The 85mm gun could penetrate Tiger armor at combat ranges. Improved transmission addressed early reliability issues. Yet the basic hull, engine, and suspension remained unchanged, allowing existing production lines to continue with minimal disruption. German attempts at similar upgrades typically required complete redesigns. Testing revealed that many T-34 components were deliberately over-engineered in specific ways, while under-engineered in others. Critical wear parts like track pins and transmission gears were designed for easy replacement. Non-critical components were designed to last the tank's expected combat life of 300 hours. German tanks were designed for 1,000-hour service life, irrelevant when average combat survival was 100 hours. Soviet designers understood statistical reality. German designers pursued theoretical perfection. The human cost of German failure to match the T-34 was staggering. Analysis of Eastern Front casualties showed German tank crew losses increased 300% after encountering T-34s. The psychological trauma was equally severe. Veterans described nightmares of green-painted slopes advancing while their shells bounced off harmlessly. Post-war interviews revealed deep professional humiliation among German engineers who had considered themselves world leaders in mechanical design. Factory 183's evacuation to Nizhny Tagil demonstrated Soviet industrial planning superiority. The entire factory was moved 2,000 kilometers east in October 1941, resuming production within 6 weeks. Workers lived in tents in -30 degrees Celsius weather, while assembling tanks in roofless buildings. Despite these conditions, production never stopped. German factories, dependent on established infrastructure and skilled workers, could never have achieved similar feats. The T-34's cost-effectiveness transformed economic warfare. Each T-34 cost approximately 193,000 rubles in 1943, equivalent to about 30,000 Reichsmarks. A Panther cost 117,100 Reichsmarks, nearly 4 times more. A Tiger cost 250,000 Reichsmarks, 8 times more. The Soviet Union could lose 3 T-34s for every Panther destroyed and still maintain economic advantage. This arithmetic of attrition doomed German efforts regardless of tactical prowess. Maintenance statistics revealed another dimension of T-34 superiority. A T-34 required 4.2 man-hours of maintenance per 100 kilometers of operation. A Panther required 10 man-hours, a Tiger 12 man-hours. In extended operations, German tanks spent increasing time in maintenance, while T-34s remained operational. Fuel consumption provided similar advantages. The T-34 consumed 1.8 litres per kilometre on roads, 2.7 cross-country. The Panther consumed 3.5 litres on roads, 5.5 cross-country. In Russia's vast spaces, these differences determined operational possibilities. Wolfgang Fischer's evolving understanding was documented in his personal notes. Initial entries showed confidence that analysis would reveal exploitable weaknesses. Middle entries showed growing respect for Soviet engineering choices. Final entries showed complete philosophical transformation. "We have been wrong about everything," he wrote in December 1941. "Wrong about what matters in war, wrong about how to design for production, wrong about the relationship between perfection and effectiveness. The T-34 is our teacher, and we are failing students." The T-34's influence extended beyond immediate military impact. It validated mass production approaches that would define post-war manufacturing. It demonstrated that designed-in simplicity could achieve better results than added complexity. It proved that understanding actual use conditions mattered more than theoretical optimization. These lessons influenced not just military design, but industrial philosophy globally. Dr. Erwin Aders spent his later years teaching engineering, using the T-34 as a case study in design constraints. The Soviets had less of everything except clarity of purpose, he would tell students. Less steel, less manufacturing capability, less skilled labor. These constraints forced innovative solutions German abundance never required. Limitation bred creativity while our resources bred complacency. The T-34's production statistics remain staggering even by modern standards. Approximately 57,000 T-34s of all variants were built during World War II. This exceeded German total tank production across all models. More remarkably, T-34 quality improved while production increased. German quality declined as production struggled to increase. By 1944, newly produced T-34-85s were more reliable than early war models, despite being built faster with less skilled labour. Post-war analysis by Allied intelligence services confirmed German engineering assessments. The T-34 represented optimal balance of firepower, protection and mobility achievable with 1940s technology. Every major military studied its lessons. The American M48, British Centurion and French AMX-30 all incorporated T-34-influenced features. Even the German Leopard 1 reflected principles German engineers had dismissed as primitive in 1941. Soviet Marshal Georgy Zhukov later reflected, "The T-34 was our army's backbone, not perfect but perfectly adequate. When we needed tanks, we had them. They worked in mud, snow and dust. They were repaired with hammers and wrenches. They were operated by boys from collective farms. This was their genius, being good enough for everything rather than perfect for one thing." Heinrich Kniepkamp, who oversaw German tank development throughout the war, admitted in his post-war interrogation, "The T-34 was the best tank of World War II. We could build better tanks for tank schools, better tanks for parades, better tanks for individual combat. But for winning a war of mass armies across vast distances, nothing matched the T-34. We learned this too late, after our fate was sealed." The philosophical divide between German and Soviet design approaches reflected deeper cultural differences. German engineering culture valued precision, complexity, and perfection. Individual excellence was paramount. Soviet engineering culture valued adequacy, simplicity, and quantity. Systematic effectiveness was paramount. The T-34 embodied Soviet philosophy, while German tanks embodied German philosophy. In total war between industrial powers, Soviet philosophy proved superior, the Kummersdorf Proving Grounds. Where German engineers first confronted the T-34 became a symbol of shattered assumptions. Here, Germany's finest technical minds discovered that their entire approach to military technology was flawed. The carefully documented tests, preserved in archives, read like stages of grief: denial, anger, bargaining, depression, and finally acceptance that Soviet designers had achieved something remarkable. Dr. Ada's final report on the T-34, written in March 1946 for American intelligence, provides a fitting conclusion. The T-34 succeeded not through individual excellence, but through systemic optimization. Every component was adequate for its purpose, no more, no less. The design was optimized for production by available workers, maintenance by available skills, operation by available crews, and combat in available conditions. German tanks were optimized for theoretical excellence that reality never provided. The T-34 won because it was designed for the war that was actually fought, not the war we imagined. The story of German engineers testing the T-34 ultimately transcends technical analysis. It represents the collision between two worldviews, two approaches to problem-solving, two definitions of excellence. The German engineers who measured, tested, and analyzed the T-34 were forced to confront the limitations of their own thinking. Their journey from dismissive superiority through grudging respect to genuine admiration mirrors the larger German experience on the Eastern Front. Wolfgang Fischer survived the war and spent his remaining years reflecting on lessons learned. His son, also an engineer, preserved his father's notebooks from the T-34 testing. The final entry, dated May 8, 1945, reads, "The T-34 taught us that elegance in engineering is not complexity but simplicity, not perfection but adequacy, not individual brilliance but systematic competence. We who thought ourselves masters were revealed as apprentices. The T-34 was not just a better tank, it was better thinking about tanks, and that made all the difference. Today, T-34s stand in museums worldwide, their sloped armour still distinctive, their simple robustness still apparent. They remain monuments not to Soviet manufacturing or Russian courage, though both were crucial, but to the power of correct design philosophy. The German engineers who tested captured T-34s in 1941 discovered a truth that echoes through military and industrial history. In warfare between nations, the side that best understands the actual problem usually defeats the side that builds the most sophisticated solution to the wrong problem. The T-34 was the right answer to the right question. German tanks were brilliant answers to the wrong questions, and in that difference lay the outcome of the largest armoured conflict in human history. The German engineers who tested the T-34 learned this lesson through measurement and calculation, through testing and analysis. Their professional integrity in acknowledging Soviet achievement, despite personal and ideological resistance, provides history's verdict on one of warfare's most influential weapons. The captured T-34 that Wolfgang Fischer examined on that July morning in 1941 represented more than enemy equipment. It was physical proof that German assumptions about racial superiority, technological advancement, and military destiny were catastrophically wrong. Every measurement he took, every test he conducted, every calculation he completed drove home a simple truth. The subhuman Slavs had outthought, outdesigned, and out-engineered the master race. The pencil trembling in his hand that morning was not from excitement of discovery, but from recognition of defeat, not just military defeat, but intellectual and philosophical defeat that would reshape how engineers thought about design for generations to come.